A sealed tank is releasing water from an outlet near the bottom of the tank. The vapor pressure within the tank above the water is 2.2 kPa, and a flow meter at the outlet measures 30 cubic meters per minute. The level of the water inside the tank is currently 10 meters from the ground, and the center of the outlet is 1.5 meters from the ground. Determine the diameter of the outlet. All right, so I'm going to write down our known information. So our flow rate at the outlet, 30 cubic meters per minute. And if we convert that to cubic meters per second, since 30 divided by 60 is a half, we have that our flow rate is 30 cubic meters per second. Now we also know that our pressure at the outlet, so let's label our outlet 0.2, label our water level inside the tank 0.1. So P2 is 2.2 kPa. All right, and we're also shown in the diagram that Z1 is 10 meters and Z2 is 1.5 meters. Now, we are going to use Bernoulli's equation to solve this problem. So, writing Bernoulli's equation, pressure divided by specific weight Here's Bernoulli's equation. Now it's important to note the assumptions that are required for using Bernoulli's equation. We're assuming steady flow, streamlined flow, inviscid fluid, in other words, negligible friction in the flow, and incompressible fluid. With those four assumptions, we may use Bernoulli's equation. Understand that the result you get is only based on the quality of your assumptions. Now, if we look at the gauge pressures, the gauge pressure at the outlet, since it's exposed to the atmosphere, is going to be 0. So P2 is 0. The internal pressure we know, 2.2 kPa. Since the diameter, or we're going to consider that the velocity of the fluid at the top of the tank is moving relatively slow. It's going to be moving very slow relative to the velocity at the outlet. So we'll consider V1 to be 0 as well. So now we have one equation with only one unknown, which is our V2. Now we're asked to solve for our diameter of the outlet, but we'll get to that after we evaluate the speed of the flow at the outlet. So if we rewrite this equation in terms of V2, I'll keep it like this for now. So I simply subtracted Z2 from both sides. Now I'm going to multiply both sides by 2g and then take the square root to get V2. Square root. And there should be an equal sign there. Okay. Now, Going to add in the numbers. Specific weight is equal to density times the gravitational constant. Just gonna make this a little straighter. Z1 is 10 meters and Z2 is 1.5 meters. Okay. Now I'll calculate. I get that the velocity at the outlet is 13.1 meters per second. Now, since we know our flow rate as well, and we're already assuming that the fluid is incompressible, we can apply the continuity equation. Continuity equation, well, really it's just the definition of the flow rate. Q is equal to V2 times A2, which is equal to V2 times pi divided by 4 times D2 squared. So now we have one equation with one unknown. So D2, solving for D2, will be 4Q divided by pi V2 square root four times 0.5 cubic meters per second divided by pi times 13.1 meters per second. Four times 0.5 divided by pi divided by 13.1 and square root. We get the diameter of this outlet is equal to 0.22 meters. So that's how you solve for the diameter of one side in such a situation by applying the Bernoulli equation. Thank you for watching. Please subscribe to the channel if you're new, and leave a comment on other content you'd like to see in this channel.